quantization means that you are promoting a field, a classical field, to a quantum field, to an operator. Remember, in first quantization, what we had, we promoted position x, momentum p, energy e, angular momentum, and other variables to operators. Okay, for example, for momentum and energy, you have relations like these, and also we insist that they should satisfy some commutation relations. For example, this one between the position and momentum. This is the first quantization. But here there's a problem. In non-relativistic quantum mechanics, this is okay, but the problem is that, well, you're treating space, x, and time not on the same footing, asymmetrically, because you're promoting position, space, to an operator, but you don't touch time. This is against the spirit of special relativity. So you have to treat space and time on the same footing. So now we try to combine special relativity with quantum mechanics to get quantum field theory. What we do, well, remembering this problem in this first quantization, but you go ahead and say that, well, look at this energy relation. Hamiltonian acting on psi, wave function, the probability amplitude should give me the energy operator acting on psi. From this, you get the Schrödinger's equation. Now you try to get a relativistic differential equation for the wave function, and you say that, well, I can use the relativistic expression for the energy, for the Hamiltonian, which is going to be something like this. And from there, you use this energy relation by squaring the previous equation, and then you get the Klein-Gordon equation. This is the Klein-Gordon equation. But it has problems. For example, it leads to negative probabilities, etc., so it doesn't work. Writing down the Klein-Gordon equation as a differential equation for the wave function doesn't work. One reason, obviously, is that you're not treating space and time on the same footing, and the other one is that, well, in this equation, you are ignoring A equals mc squared. If you have enough energy, you are treating, a system which is relativistic. You are talking about high energy particles, so you're going to have enough kinetic energy to create new particles according to E equals mc squared. So writing this m here is kind of problematic, because you are assuming that you are working with one particle or a fixed number of particles. So instead, one solution is that you should interpret the psi, the solution of the Klein-Gordon equation, not as a wave function, but as a field. Okay, it's a classical field. It gives you some quantity in space and time at x and t. It's similar to, for example, the equation for the vector potential in electromagnetism. In vacuum, you get something like this, and the mass of photon is 0. So in the right-hand side, you have 0, but here in Klein-Gordon case, you are working with a particle with mass m, so we have non-zero right-hand side. So the second quantization is that these quantities, phi and a, should be promoted to operators, and then you're going to add some commutation relations. For example, something like this. This is called second quantization. Okay, so remember that here we didn't touch space and we didn't touch time. Space and time, like classical mechanics, are just labels. Fields are being promoted to operators. So, for example, if you remember from non-relativistic quantum mechanics, wave function psi is defined as an inner product between position eigenstate x and the quantum state psi from the Hilbert space. But no one tells you what this x is. How you create a particle at position x, right? Here you go. We have some answer to this. If you apply this now quantum field operated solution of the Klein-Gordon equation basically as an operator, acting on vacuum, the quantum state when there is no particle, it gives you a particle at position x, and it's the meaning of this eigenstate here. So this process of promoting a classical field by phi, or for A in electrodynamics, which is going to give you quantum electrodynamics, is called the second quantization.